Number 6. This is a throwback for me. We're looking at velocity graph. You're asked to kind of explain situations based on the graph that you're seeing here, right? So there's a student that's claiming that the cart moves a greater distance from 0 to 4, so from 0 to this point here, than it does from 16 to 20. So during this section here, right? So we're comparing these two sections. And that's because the cart's displacement during this interval from 16 to 20 is negative. So that displacement is indeed negative. Okay. But the value, right, if you were to calculate the areas of these two sections, they would be the same. The displacement is the same for both, right? One's just negative, but we're not asked about displacement, we're asked about distance. Right? And distance doesn't care about which sign you have. So they both have a total area of about, is it 4 times 4 times, so it'd be 8, right? Area here is 8, area here is 8, they're the same, right? But they're right that displacement in the second part is negative. So this is correct, right? But it does not move a greater distance. It's incorrect. They move the same distance. Because the areas you can see are equivalent. Distance doesn't matter. Distance doesn't care about sign. So B, which aspects of students' reasoning, if any, are incorrect? Like I said, basically they have the same distance. So that's correct. So I guess this would go down here. And we would just talk about calculating the area and then explaining that distance is the scalar. It doesn't have, does not depend on sign. Okay. Describe how the graph could be used to find the acceleration at t equals 9 seconds. 9 seconds would be right here. So we want to find the acceleration at that point there. Acceleration is the change in velocity over the change in time. We can find the average acceleration that way. So we can find the difference between the velocities that do points 8 and 10 seconds, right? So it's a straight line. And then divide by the time, right? Basically what we're doing here is finding the slope. So you could say find the slope, rate of change at t equal to 9 seconds. And that is the acceleration. So we're supposed to graph the acceleration of the cart from t0 to 20 seconds, then label everything, including units. It's not something that you guys have practiced, but I'll very quickly kind of explain it. You're rarely asked to do this kind of thing. So going downwards like this is your y-axis, this is our x-axis. Let's say this is 5 seconds, 10 seconds. Actually, let's do 10 seconds. Let's do 5 here, 10, 20, 30. Okay, and we'll do 1, 2, and then 3, -1, -2, -3. This is acceleration in meters per second squared, and then this is time in seconds. Okay, that's all the labels we need to add. Now we just need to actually do the calculations. Basically find the slope at each section and then graph that. Right, acceleration is always constant in these graphs. You can see there's no curves in the velocity graph, so each of these values is going to be a flat line, just at different points. So from 0 to 4, the slope there is 1. So we just draw a line from 0 to 4 at 1. I know I'm going to be off by a little bit here. Just kind of bear with me. It's not going to be perfect. And then from 4 to 8, the slope is 0. So I can go from 4 to 8. We had 0. And then from 8 to 10, it's going to be a negative slope, and it's going to be 2. So -2 from 8 to 10. Then from 10 to 14, it's 0 again. So going like this. So 1, 2, 3, 4. I missed something here. Yeah, my axes are labeled wrong, but I'll get to it. 14. So this is supposed to be 15. This is supposed to be 20. This is probably a bad idea because I'm gonna have to go 25 and then 30. Okay. Oh well. All right, so it only goes up to 20 here. I'm crazy. Okay. And then from 14 to 16, it goes down -1. So 14, 16, down -1. And then from 16 to 20, it's 0. Like this. Okay. That's the acceleration that graph looks like. I know it's not super interesting or even like intuitive, but all we're doing is graphing the slopes from the velocity graph. So at the very least, just remember that the slope of a velocity graph is the acceleration. And then this is what constant values look like on a graph. Describe how the velocity time graph could be used to sketch the position time graph of the cart. Well, you could calculate the areas, the graph, to determine displacement. I think that's a good enough explanation. And then F, sketch the position time graph for the card from 0 to 20 seconds. All right. 0. This. This is a sketch, so we don't need to be like super detailed with the values or anything. Basically, at the beginning here, you can see the velocity is increasing. For the first 2 seconds, it only climbs a little bit, so it's about half of a block here, so it's 1 meter basically. And then in the second 2 seconds, it climbs, that's 4 meters, 5 meters. Right, so there's an acceleration that happens initially, and then velocity kind of becomes constant. So initially you have the velocity accelerates, and then there's constant, right? Then it becomes negative velocity. So as it starts to curve downwards, okay, eventually hit 0. That's where the peak is at 10 seconds, and it remains at 0 for a few seconds, and then it becomes more negative, and then it remains at that negative rate the entire time. So you kind of get a straight line. Kind of looks like that. I would never ask you to do something this elaborate, but it's nice to know that it's possible. Okay. So just to clarify here, so you can illustrate sort of what I'm pointing at here. This section here where it's increasing in velocity, right? That would be here, where it's at a constant velocity. That would be around here. Then as it's slowing down, right, heading back to 0 velocity, that would be that curve there, and it stays at that velocity for a bit. So it would stay flat like this. And then it would start to go negative. So that little curve there. And then the last bit, where it stays at some negative value constantly, like this. Okay. So this is a rough sketch. It's not supposed to be perfect.